Alright, so a couple more problems from this problem set I actually want to look at with you guys. Solving an equation like this is challenging. If you only had one square root, let's actually think about that first. So if I only had one square root equals 5, we can think of it just like backtracking. So all we got to do is square both sides to eliminate the square root, and then you can just add 12, right? But here we've got two square roots, and we're going to run into situations like this. So I like that we're looking at this kind of equation here just because since we're working with things involving distances and we're going to be using distance formulas, some of our definitions will require us to use the distance formula twice, which means we have two square roots, and then simplifying that is kind of ugly, but it's doable. So this will help us ease into that process. So if I have this, here's how we deal with this. We're going to actually square some stuff, but we're going to end up having to square it twice. Typically for me, I like to move everything over here, I like to move one of the square roots over, and what I'm then going to do is what we said originally, which is squaring both sides. And what that's going to do for me here is it's going to eliminate the square root over here. But over here it's not quite, and it's going to be a little bit of a trick, but let's just see what happens. So this is just x minus 12 equals. Now, on the side, don't forget this pattern here. If a minus b is squared, then we have a squared minus 2ab plus b squared. Okay, so just on the side, keep that in mind. What's behaving like our a and our b here? Our a is 5 and our b is this square root. So if you just kind of keep in mind that pattern, then we can expand that out and get it to work. So this becomes a squared is 5 squared, so 25, minus 2ab, so minus 2 times 5 is 10, so minus 10 times root x minus 7. And then that's a negative, but when you square it, it gets positive, right? And then you square the square root, so we have plus what's underneath there, which is x minus 7. So now let's shore things up a little bit. Nice thing here is we subtract the x's off, they're gone. I think we can subtract the 25 and add the 7. In fact, let's do this. 25 minus 7 is 18. And if we subtract 18 off of here, we get negative 30 equals negative 10 root x minus 7. And this actually seems a little bit more doable. Again, we can think of it kind of like backtracking. If I divide both sides by negative 10, I'll get positive 3 equals root x minus 7. Square both sides to get 9 equals x minus 7, and therefore it seems like I get x equals 16. So it's kind of a long algebra process. However, this step here is crucial in remembering this pattern. And even if this is adding right here, then this just becomes plus and plus, right? So just don't forget this perfect square pattern from before. Okay, so that's number 6 that I wanted to look at with you guys. And you can always double check this, by the way. If you plug 16 into here, then this becomes 4. And square root of 4 is 2. And 16 minus 7 is 9. Square root of that is 3. 2 plus 3 equals 5. And it does happen to work. Some weird stuff can happen when you're dealing with roots, which we'll probably bring up later on. But when you have to square things, sometimes you can create extraneous solutions or extra solutions that may not work. In this case, we didn't get anything that we had to square and square root again or anything to solve, so we didn't end up with anything extra or weird. So this one worked out okay. The next one I wanted to look at with you actually is question, well, we can take a look at question 7 for a moment. I'm gonna flip over here to the textbook. I want you to, I gave something away here, but I want you to notice a few things. These all are really similar, kind of like when we looked at number 4, I believe it was. This is just simply a circle whose center is at the origin with radius 5, so you can easily sketch that graph yourself. And then each one of these, notice on the right side, each one of these has 25. So they seem like they're all circles with radius with radius 5, but their centers are just located in different places. Now, one thing interesting is I want to point out 7e. This is not put in a format that you maybe are used to seeing, but notice how these two have the same denominator. If we multiply that through on both sides, you could actually see that we get x squared plus y squared equals 5 squared would be over here, right, which is 25. And it actually turns out to be the same equation as A. We're going to be looking at equations that actually look like this form here in 7e as we go through this investigation. So I just wanted to point that out and get you a little familiar with it. And then the last one that we didn't look at in class today that I wanted to look at with you is this one here, 6.5, question 9. So imagine you're on a camping trip. You're returning from a hike in the woods, and you see, oh no, my tent's on fire. This is a silly question. Luckily, you're holding an empty bucket, just so happens, and you're near a river, so you plan to run to the river first to fill the bucket, and then run to the tent. This is not, by the way, meant to be a very realistic problem, guys. It's just kind of silly on purpose. But there is an important mathematical truth that is happening here. Now it says in CME project geometry, you probably didn't actually use that for geometry, but that's okay. The shortest total path reflecting y over the line. There's something interesting, and I hate to just give this away right now, but it's a cool problem. Actually, I think it's a really cool problem to talk about here. I'm going to sort of redraw this diagram. If I need to be at, I'll use the same labels here. If I need to be from point Y to point T, but I need to visit the line first, what's the shortest distance? Now it's tempting to say the shortest distance is just straight down because that is the shortest distance from Y to the line. But then we have to go to T. Now is that total distance the shortest now? See what I'm saying? And remember, there's a ton of options. Like you could go down here, straight down and across, but you could also go here and up, and you can see that definitely this distance is shorter than it was over here, and so maybe the total is now less. But the question is, and maybe even this total is less, you never know. It turns out there's a really cool solution to this problem, and that is that, I'm going to redraw this again. Again, if we have, let's say, y up here and t down here, let's ignore the line here. What's the shortest distance between any 2 points always? A straight line, right? One thing that's super crazy is this point we'll call P, maybe we'll call P1, P2, P3 up here. It turns out if we reflect y across this line here, and watch, if you take T to P to Y again, that's going to actually represent the shortest point. So watch this really awesome trick. If I take Y and reflect it across here, let's say it's right there, and we'll just call this Y prime, that's what we usually do. And then what we'll do is we will just connect Y and T together. This right here represents the P that I want, because look at this, YP, that's the same length as Y prime P, because we just reflected it across. And so since this is the shortest distance from T to Y prime, this P value must be the shortest distance to get from Y to P to T. It's a really, really cool thing. So that actually is what they're talking about here in 9a. And it says, explain why this method produces the shortest path. Well, I kind of just did for you, so that sort of answers part A. Now, part B says you also looked at contour lines, which we haven't defined here for the situation, and I don't think you've probably looked at that before. It's the collection of all points for which the path YPT has the same length. So if we were instead thinking about taking this, okay, YPT, and in fact, actually, let's go back to the one that's the one we want, and I'll actually color this in blue now, because that's actually going to be my shortest path. So if I actually fix this total distance to be the same, this point P would actually not be on that line anymore, it would kind of go elsewhere. But for now, I just wanted to kind of get you thinking about this interesting problem, and it actually relates to a lot of what we're going to study. We're not going to worry about parts B and C, really just part A is the only one that I included there for you, but this is a really cool problem. So that's it for the rest of what I wanted to look at. You'll see in question 10 that there's a similar problem as we did in 6, so that'll give you a little bit of practice on that, doing it yourself. And then the honest truth is, if you wanted to just make up more, if you think you need more practice on it, you can, but we'll be getting more later. So that'll do for today, and I'll talk to you later.